Today on The Hookup, I'm going to show you everything that you need to know to get set up with permanently installed holiday LEDs in November of 2021. 4 years ago, I installed LEDs on the roof line of my house, and at this point, I've made about half a dozen videos explaining different parts of the LED installation process. There's still a lot of good information in those videos, but so much has changed to make the process both easier and better. This video is going to have an overview of everything that you need to know, all the choices that you need to make, and all the improvements that have happened over the last 4 years. This is a really long video, so feel free to use the chapter markers to skip around, and make sure you hit the like button if your question gets answered. This video was sponsored by WLED and their new flexible configuration LED wall panels. WLED is known for their high saturation LED colors, and these new wall panels definitely keep with that trend. Each kit comes with 6 panels that can be configured into different designs, and up to 12 panels can be controlled by each effect module. These panels work with the Xiaomi Mi Home app, meaning they're easily added to your favorite smart home control platforms like Google Home, Amazon Echo, Samsung SmartThings, Razer Chroma, and even Home Assistant. With built-in effects, millions of colors, and sound reactivity, these panels turn a boring corner into awesome accent lighting in just a few minutes of setup. Check out the newly released WLED wall panels using the link down in the description. Let's start with the most basic question: pixel strings or strips? For a clean-looking install, LED strips can be mounted in aluminum channels with white diffusers, and pixel strings can be installed either in drilled-out J-channel from a big box store or in purpose-built mounting solutions like Dr. Z's Permatrack. Ultimately, this choice comes down to aesthetics and your personal preference. But for me, I went with strips because I wanted them to point out towards the road, and I wanted to be able to completely conceal them in aluminum channels. The LED density of a strip will typically be greater, so the animations look a little bit smoother from head on. But if you want your LEDs pointed towards the house for a more indirect effect, then strips versus strings doesn't make as big of a difference. From a durability standpoint, pixel strings and strips are about the same as long as they are permanently installed. However, if you're planning on taking your LEDs up and down or moving them around, you should definitely avoid strips because they tend to be more delicate once they're installed. Pixel strings are also easier to fix if an LED goes bad, since it's easier to cut out a couple of pixels than it is to replace an entire section of LED strip. Both are totally possible, but soldering on a ladder isn't the most fun thing to do. That being said, my strips have been up for 4 years and have only required one minor repair caused by a lightning strike, but your mileage may vary. Once you've decided on pixel strings or strips, you need to pick a voltage, 5 volts or 12 volts. Without getting too complicated, voltage is how hard the electricity gets pushed through a wire. Using 12 volts will mean that you have less power injection, which we'll cover later, and you'll have the ability to push more electrons through a smaller wire size. But that comes with a safety trade-off. I've done lots of experiments showing that it's extremely difficult to cause an electrical fire with 5 volts, even with a dead short, while a 12 volt system has enough push behind those electrons to heat up a wire and cause plastic to melt and smoke. In online forums and Facebook groups, I've seen plenty of examples of corrugated plastic props that have caught on fire due to faulty 12 volt pixels, but I've never seen a 5 volt pixel fire. If you're at all concerned about LEDs burning down your house, which by the way I've never heard of, then 5 volt LEDs are safer than 12 volt LEDs. As for the type of pixels, if you choose strings, you're most likely going to end up with WS2811 pixels, which you can choose 5 volts or 12 volts. But if you choose strips, you're going to be a little bit more constrained by your voltage choice. The most popular and readily available 5 volt LED strips are WS2812B strips, and for 12 volt strips, you should use WS2815 strips, which are pretty pricey compared to WS2812Bs. You can also get 12 volt strips that are made with the WS2811 chips for pretty cheap, but they're only going to be controllable in banks of 3 LEDs, instead of being individually controllable, which for indirect lighting is probably fine, but for LEDs that point out towards the street, you're going to want to be able to control each individual LED. One last option that exists for strips is the RGBW strip variety that adds a dedicated white channel. If you're planning on using these strips for ambient lighting year-round, this might be a good option, but you should expect to need more maintenance for your system if you're running them every single night. The RGBW variety is called the SK6812, and they exist in both 5 volt and 12 volt varieties, although the 12 volt kind is like the WS2811s that are only controllable in banks of 3. As for waterproofing, I've used all the different types, and by far the one that I've had the most luck with are the IP65 version, where the strip is coated in silicone rather than being installed inside of a silicone tube. The biggest point of failure that I've seen in the IP65 strips comes when you have freezing dew that gets in between the strip and the aluminum channel and causes it to short out. If you have a lot of cold weather in your area, it is worth putting a strip of electrical tape in your LED channel before installing the LED strips. The last thing to consider when ordering your LEDs is pixel density. When using pixel strings, the minimum density will usually be 70 millimeters or 2 3/4 inches because the wiring in between the pixels is usually 3 inches long. You can order custom spacing if you go directly from the manufacturer, but if you buy from Amazon or AliExpress, you're usually just going to get 3-inch spacing. I use pixel strings for my seasonal lighting around my doors and windows, and I drilled holes in a PVC conduit about 2 3/4 inches on center to make frames that are easy to install and remove. For strips, I'd highly recommend getting the 30 LED per meter variety, where the LEDs are spaced 32 millimeters or 1 1/4 inches on center. If you want to get really crazy, you could use the 60 LEDs per meter, but keep in mind that if you double the number of LEDs, you're also going to double your power draw, which leads me to the topic of power supplies. When choosing a power supply, a general rule is to budget 50 milliamps or 0.05 amps per 5 volt LED and 30 milliamps or 0.03 amps per 12 volt LED. So a 5 volt 50 amp power supply should be able to drive 1,000 5 volt LEDs, and for 1,000 12 volt LEDs, you'd need a 12 volt 30 amp supply. It's also important to note that in the real world, 1,000 5 volt LEDs is never going to pull anywhere close to 50 amps. But since you also shouldn't continuously run a power supply at its max current, the overestimation of milliamps per LED works out well. If you want to go straight to the best quality power supply, then you should look for the Meanwell brand name. But I've had really good luck with my cheap generic power supplies that are still going strong after 4 years. For wiring both strings and strips, I'd recommend using 18 gauge 3-core wire, and my current favorite type is this RVV wire that has a nice thick PVC jacket that seems to hold up really well to the elements. I'll link the specific one that I use down in the description. Next, let's talk about joining your LEDs together. If you're using pixel strings, they come with these connectors on the end, which would let you just clip each string together. However, these connections are not waterproof, so if you're doing a permanent LED install, you should replace them, and I recommend using solder seal butt connectors. To do this, just strip off about 1/2 inch of wire on each end and then slide the butt connector over one of the wires. Then make a loop on each end of the stripped wire and hook the 2 loops together and twist. Then slide the butt connector over the connection and heat it up with a lighter. You should see the heat shrink tubing conform to the wire, the colored waterproofing melt and seal each side, and the solder should flow onto your stripped wires. These things are very waterproof, and I just leave mine completely exposed, but if you want to, you could wrap them in electrical tape or heat shrink tubing for extra protection. You'd also use the same process for injecting power into pixel strings, which again, we'll talk more about later. Joining LED strips isn't quite as easy, but in my opinion, there is one best way to do it. For each straight section of your roof, you should pre-measure the exact length of LED strip that you'll need, so you don't need to do any cutting or soldering on the ladder. To join 2 IP65 waterproof strips together, start by peeling back the silicone covering. The best way to do this without damaging the strip is to use a pair of nippers to cut down into the covering and then peel the covering towards the cut end of the strip. Don't peel from the cut end because you could easily lift up the soldering pads and ruin that part of the strip. I recommend sacrificing 1 pixel so you have 1 full pad to solder onto. Start by putting a section of 3/4 inch heat shrink tubing over one side of the strip. Then stick your full pad onto a heat resistant surface. Use the adhesive back to stick the half pad on top and lay a thick bead of solder across each of the pad junctions. After that, fill the entire exposed space with hot glue and slide the heat shrink tubing over it. When you heat up the heat shrink with a lighter, the hot glue will melt again and seal up the entire connection. To go around corners, it's okay to bend the strip from front to back, but you shouldn't try to bend it from side to side. So to make angles like on the peak of a roof, you should cut the strip and remove the silicone covering like before. I like to use the wire that comes on the ends of the strips to make these junctions because it's nice and flexible. Before you start soldering, slide a 3/4 inch heat shrink tubing over both ends of the strip. Then add a bead of solder onto each pad. Then tin the ends of the wire and apply a little bit of heat to each pad to join the wire and the pad. Cover the exposed area in hot glue, and then use your lighter on the heat shrink tubing to seal up the junction. Anytime I make a junction, I always add a power injection point. If it's a corner junction like this, then just add an extra set of wires, but if it's a strip connection, I use 2 pads that are at least 1 LED away from the junction. By using a set of pads away from the strip junction, it reduces the chances of those solder joints breaking. To make a power injection point, cut down in the silicone covering like before, and add a bead of solder to the positive voltage pad and the ground pad. Tin the ends of some 18 gauge copper wire and attach them to the pads. Fill the exposed spaces with hot glue and then slide heat shrink tubing over the whole thing and use a lighter to shrink it down and remelt the hot glue. Now you have some easy leads to inject power using solder seal butt connectors, so you don't need to do any soldering up on a ladder. Speaking of power injection, what is it and how do you do it? Well, when you have a long string of LEDs powered from a single location, the voltage available to each LED is going to decrease as you move further down the strip. This is caused by the fact that all of the power is going to go through two tiny strips of copper inside the LED strip instead of some thick wiring. As I mentioned before, using 12-volt strips will allow you to push more electrons through these tiny wires, but you're still going to need to inject power if you're planning on lighting up your entire roof line. As a general rule, 5-volt strips should be powered at the beginning and the end of every 5-meter strip, and 12-volt strips can be powered at the beginning and end of every 2 strips. The most effective type of power injection is called home run injection, where you run a separate power wire from the power supply to each injection point. In my case, I only have one convenient spot to wire a home run, so I make do with what are called parallel injections that go inside the aluminum channel. The idea behind a parallel run is simple. Inside the strip, you have a single small copper pad carrying all the current. By adding a parallel wire, you are at least doubling the amount of current that can travel through the same distance. The wire I'm using is very thin 22 gauge solid core wire, and it's connected to each strip both at the beginning and the end. By using a combination of these parallel runs with my single home run, I'm able to achieve accurate and bright colors on my entire 473 first floor 5-volt LEDs. On my second floor roof line, it doesn't have any good injection points, so I'm only using the parallel injection method. And with 381 LEDs, I'm still able to get good color accuracy as long as I limit the brightness to about 75% in software. What software, you might ask? Well, the LED lighting hobby used to be clearly divided between people who sequenced full-out shows and people who wanted a low-key setup with some animations that they could control on their phone. Unfortunately, these two setups used completely different hardware, so if you ever wanted to jump between the two, you'd need to replace a lot of your electronics. But in 2021, that is not the case anymore. A combination of faster microcontrollers in the form of the ESP32 and absolutely amazing development by AirCookie and the rest of the WLED team has blurred the lines between the two groups, and now you can do everything with a single setup. For permanently installed LEDs, there is no better hardware option than the Quinn LED Dig Uno or Dig Quad, depending on how many LEDs you have. The Dig Uno can support up to 15 amps of continuous draw from 5-volt or 12-volt LEDs, which would correspond to about 300 5-volt LEDs or 600 12-volt LEDs. But you'll see in a minute that you can actually drive significantly more than that using the brightness limiter in the WLED software. If you need more LED outputs or more power, the Dig Quad bumps you up to 4 data outputs and up to 30 amps of continuous draw. The Dig Uno and Dig Quad also have built-in level shifters to make sure that your LED data works properly. They've got fused power outputs for extra safety and a built-in voltage regulator so you can power the board with 5 volts or 12 volts without needing any extra electronics. So all you do is buy the correct power supply for your LED voltage, and the Dig Uno or Dig Quad will work with that power supply. But the most important part about the Dig Uno and Dig Quad is the fact that they come with an ESP32 microcontroller pre-installed with the super powerful WLED controller software. And that means you won't have to do any programming at all to get your LED set up. The Quinn ESP32 comes in 3 variants, one with a built-in antenna, one with an external antenna, and my favorite one, and the one that I would absolutely recommend to you, is the Ethernet variety. Using Ethernet future-proofs you for down the line when you inevitably want to try out a music sequence show, since sending your light show data over Wi-Fi is a pretty bad plan. To hook up your Dig Uno or Dig Quad, start by pulling the ESP32 board off of the power supply delivery board. There's a small plastic piece that covers the unused pins on the right side. It's not a big deal if it falls off. On the Dig Uno, there is a single power in and a single power out with 1 fuse. This fuse should be sized for your specific LED installation. So if you're going to be pushing it to the maximum current, then you should replace the 10 amp fuse with a 15 amp fuse. Your data line is going to connect to the LED 1 terminal unless you want to have 2 different lines off a single Dig Uno, in which case you'd hook up both the LED 1 and the LED 2 terminals. If you're using a Dig Quad, there are significantly more power output terminals, all with separate fuses, and each terminal can handle up to 10 amps. In my first floor setup, I have my main power and my home run injection set up on terminals 1 and 2, which share a 10 amp fuse. But if I wanted to be able to supply as much as 20 amps, I could run the main power off terminal 1 and the injection through terminal 3, which is on a separate 10 amp fuse. If you want to run the maximum current through your Dig Quad, make sure you're using the correct size cables to feed the board. If you've got the V1 or V2 versions of the Dig Quad, you'll want to connect at least 2 of the input terminals with at least 18 gauge wire. If you've got the new V3 board, you can connect a much thicker wire like this flexible 12 gauge, which can supply plenty of current. For a clean looking install, I also like to use ferrules on the end of my stranded lines before attaching them to the screw terminals, but it's not a totally necessary expense. About the only thing that I don't like about the Dig Quad and the Dig Uno is the fact that they use resistors on the data lines. A long time ago, Adafruit posted a best practices blog about hooking up addressable LEDs, and they recommended putting a 300 to 500 ohm resistor on the data line to prevent spikes in data that could damage the first pixel. However, in all of my LED projects, the only thing that's ever damaged the first pixel on one of my strips was a lightning strike, which I don't think a resistor would have helped. And unfortunately, I've experienced lots of data corruption issues when using a resistor on data lines that are longer than a few feet. You can either desolder the 249 ohm resistor and replace it with wire or a solder bridge, or you can use one of Quindoor's data boosters that lets you select between the 249 ohm resistor or a 33 ohm resistor to fix those data issues. Both options worked well for me, so if you see your LED strip freaking out during animations or sometimes just not coming on at all, the resistor on the data line is likely the culprit. So last, that brings me to the star of the show, WLED. I have written 2 versions of my LED control software and 1 version of my RGBW light bulb control software, and I'm very happy to report that no one should use either of them anymore. WLED is a better solution in every single way. Not only is it more powerful, easier to set up, and easier to control, but AirCookie is a real developer and is constantly making updates to the software to make it better. Let's take a look at some of the most important parts of WLED. When you first connect your WLED device to power, it's going to broadcast an access point so that you can set up your Wi-Fi information. Connect to the WLED Wi-Fi network using the password WLED1234, and a browser window should automatically open up. But if it doesn't, you can go to 4.3.2.1 in your browser and enter your Wi-Fi information. If you're using the Ethernet version of the Quinn ESP32, you get to skip this step and just plug in your Ethernet cable. Next, find WLED's IP address on your router or using an app like Fing, and then connect to that IP in your browser. If you've got a lot of screen real estate, the first thing that you should do is click on PC mode so that you can see all the tabs at once. The first thing we need to do is set up our LEDs, so click on Config and then LED Preferences. Depending on the version of WLED that you're using, you may see a spot to put in the total number of LEDs at the top, or just a readout of the total number of LEDs that you have set up in outputs. But below that, you have your different outputs and the pins that they correspond to on the ESP32. If you got a Quinn LED Dig board, these outputs are going to be already set up for you, which is 16 and 3 on the Dig Uno, or 16, 3, 1, and 4 on the Dig Quad. For each output, select the type of LED that you have, which is most likely WS281X variety, and then put in the number of LEDs that you have connected to each output. In WLED version 13 and above, the start channel is going to be automatically calculated for you, but if you have 12 or below, you're going to need to do a little bit of math. This is also the page where you need to decide if you're going to use the brightness limiter, which in my opinion is one of the most impressive features in WLED, and to my knowledge it isn't found in any other software. The concept for it is pretty simple though. If you want to run your LEDs at full brightness white, WLED is going to calculate the number of amps that would pull using the estimate of 55 milliamps per LED on full brightness white. If you had a total of 1,000 LEDs, you would need 55 amps at full brightness white. But if you have the brightness limiter set to say 30 amps, it would only allow those lights to come on at 55% brightness, so they would only pull a maximum of 30 amps. Not only does this add a layer of safety, but it also helps prevent color inaccuracies due to voltage drop. Once you've got your LED page set up, you're ready to start blinking some lights. Go back to the WLED main page and you'll see 4 different panes in PC mode. On the left is your color picker, where you can choose from dozens of pre-made color palettes or make your own by selecting up to 3 colors from the color wheel. These colors will be applied in different ways to all the patterns, which you can find in the next pane. Each pattern has 2 modifiers that may or may not apply to it. The first one is the speed modifier, which as you'd expect generally changes how fast the pattern moves, and the second one is the intensity, which usually changes how often the pattern repeats. But sometimes the sliders do less intuitive things, so it's worth playing around with them to get the pattern just the way you want it. Next over is the segments pane, which is where you can define specific parts of your house. So instead of the pattern repeating over every connected LED, it only shows within that one section. For instance, I've posted my Halloween LEDs on Twitter a few times, and people always ask me how I make the fire pattern look the way it does. Because if you just choose Fire 2012, you're going to be pretty underwhelmed by the results. But to make the fire look convincing, I make each angle on my roof a separate segment. And then I make sure that the start of the segment is always the bottom by hitting the reverse direction button on segments where a higher LED number is closer to the ground. For my LED wreaths, I take the total number of LEDs in each circle divided by 2, and I make 2 segments per circle. After that, I apply the Fire 2012 effect and tweak the speed and intensity until it looks the way that I want to. You can also individually change the speed and intensity of each segment by clicking the check marks next to the segments. In this case, it's only going to apply the changes that I make to the segments that are checked. One thing to note about that, if you're using the latest stable release of WLED, which is 12.0 at the time of this video release, then you're going to be limited to 16 segments, and you can't rename them. But as of WLED 13.0, the ESP32 supports 32 segments and also adds the ability to name your segments. And if you're watching this a year from now, WLED is probably 10 times more amazing. Moving on, After you've taken all the time to make those segments, you want to be able to use them in a bunch of different ways. So you should save them into a preset. To do this, click on New Preset and then give it a name. Make sure that all 3 boxes are checked, including the one about saving the segment bounds. This way, if you want to make a new effect with the same segments, you can just start with this preset, change the effects, and then save it as a new preset without overwriting your old one. And the last reason why WLED is so amazing is how flexible it is. As I mentioned earlier, for years, if you wanted a low-key setup to do some animations on your phone, you would choose an ESP8266 based microcontroller to select those patterns. But if you wanted to do a whole light show sequence to music, you'd need to buy an entire separate controller like the Falcon F16B3, a Hinx Pro, or a Culp board. But WLED and the Ethernet ESP32 have changed all of that. In WLED, if you click on Config and then Sync Interfaces, you can see exactly how flexible WLED is. It can be set up to use a physical button. One WLED controller can control another one. It can be discovered and automatically controlled by Home Assistant. It can receive and process DMX inputs through the E131 format or DDP, which are both used by X-Lights to make synced musical light shows. You can control WLED directly with Amazon Echo devices, you can use MQTT or the Blink protocol, and you can even add WLED to your Philips Hue app to work alongside of your Hue lighting. I'm not going to go over all the details of making a light show in this video, but rest assured that if you do decide to jump into the hobby, that you won't need to replace your DigQuad or WLED. I'm not saying that controllers like the Falcon F16V3 or the Hinx Pro are obsolete. They're definitely still useful when you have dozens of outputs like on a Megatree or a large matrix, but it's great to see that it's easier to move between the 2 controller types now. I've got absolutely tons of links down in the description for my recommended vendors and LED listings, and those are affiliate links, so if you appreciate a video like this, consider using them since I get a small percentage of the sale at no cost to you. Thank you so much to my awesome patrons over at Patreon for your continued support of my channel, and if you're interested in supporting my channel, please check out the links down in the description. If you enjoyed this video, make sure you hit that thumbs up button so YouTube knows it's a good one, and consider subscribing. And as always, thanks for watching The Hookup.